All right. Thank you for joining us for our colloquium today. It's my pleasure to introduce Francisco Mercado. Francisco got his PhD at UC Irvine. Before that, he got his bachelor's at Cal Poly Pomona. He is now an NSF MPS Ascending Postdoc Fellow at Pomona College. And he has a broad range of expertise related to galaxy evolution, galaxy dynamics, and chemical enrichment. In addition, he's very passionate about mentoring and bringing astronomy to the next generation of astronomers, in particular marginalized groups. So I really hope you guys take advantage of having him visiting today. So anyway, take it away, Francisco.
Yeah, thanks, Tony. It's great to be here today. I think my mic is on. I think, yeah, looks good. Yeah, so thank you all for having me today. I'm very excited to get to talk to you all about some work that I've done at UC Irvine and also some work that I'm continuing as an MPS Ascend Fellow at Pomona College and visiting at Caltech. So specifically, I'm going to talk to you all about nature versus nurture and really how internal versus external processes can shape galactic interiors. So real quick, I'd like to start with an outline. I'm going to just give a quick introduction to what I do and the questions that I am really interested in answering. Then I'll follow up by talking about the answer to the sort of nature question. And this is mostly work that I've done in the past at UC Irvine. Then I'll follow and talk a little bit more about the nurture side of things. And that's work that I'm doing now as an NSF fellow. And then at the very end, I like to talk to you all about the Astro Uplift project, which is some of the proposed broader impacts work for the NSF that I'm really excited about. So I'm really happy to be here to chat with you all about all of this. So as I mentioned, we're going to talk about a couple of different things. Nature, which is really internal processes that might affect galactic interiors, and external processes, which are going to be the nature part of things here. So a couple of examples of processes that might affect the internal structure of galaxies, at least from the nature perspective, right? That is, we could think about star formation feedback. So, right, if we have stars forming at the center of galaxies and then going supernova, they can impact the galactic interiors that it's happening in. Another example of this might be AGN feedback, right? This is sort of at a larger scale that this might be impacting a galaxy. On the other hand, you might have processes like interactions with a galaxy's environment. That's part of your sort of external processes or the nature that I'll be talking about, or excuse me, the nurture side of things. And then finally, potentially cosmic ray ionization, right? And so all of these processes come together to really make one fact abundantly clear, and that is that galaxies are very complex systems. So what we're looking at here is a zoom-in simulation of a Milky Way-ish mass galaxy in a cosmological environment. This is particularly one of the this is the feedback in realistic environments simulations. And right off the bat, what we see is that you get these sort of outflows coming from, at least within the fire simulations, this sort of star formation feedback, and it's really impacting the internal structure of the galaxy. Then you start to see some of these mergers come in, right? And this is sort of some of the nurture portion of what we'll be talking about. And so these are interactions with a galaxy's environment. And all of these processes come together to play a role in really shaping the internal structure of these galaxies, right? So while you know, I hope that at least watching this video really has us convinced that galaxies are indeed very, very complex systems that have a ton of factors that are impacting what they look like, you know, today. And I'll let that finish. It should be finishing up soon, but you know, you get some of these things. But despite being very complex systems and despite having very chaotic lives, these galaxies follow some very remarkably tight scaling relations. Some of these scaling relations that some of us here might be very familiar with, like the Tully-Fisher relation, which connects a galaxy's asymptotic velocity to the brightness or the mass of that galaxy. The gradient strength galaxy age relation, which we'll hear a little bit more about later in this talk, but that connects a galaxy's stellar metallicity gradient to its age of the stars that make up that galaxy. Mass-Metallicity relation, which is exactly what it sounds like, the connection between a galaxy's mass and the average metallicity. and then the radial acceleration relation. Now, scaling relations are very important to me because they can help us really connect the observable properties of galaxies to the processes that shape them, right? And so the big question that I'd like to answer really, or the question that I'm asking is how do internal versus external processes really shape galactic interiors in such a way that they fall on different regions of these scaling relations? So the question here is what role do internal versus external processes play in determining the position of a given galaxy on these scaling relations? Now, in the past, a lot of my work has been really, the subject of my work has been these two scaling relations here. This is work that I've done at UC Irvine, so really looking at the gradient strength galaxy age relation and the radial acceleration relation. I'm going to go ahead and talk about this work that I've done so far today. And I'm going to show that, at least for these two scaling relations, they arise primarily due to their nature. And I'll show you how we do this. So to answer this question, I look at zoom-in simulations, really to understand the nature of these galaxies. So a little bit about the simulations that I work with. As I mentioned before, or as I've shown you all before, the fire galaxies are what I use. And so this is sort of a suite of zoom-in simulations in a cosmological environment. These galaxies are high-resolution simulations in their environments. They produce a resolved multi-phase gas, which we could see on the left-hand panels here of the different galaxies we're looking at. They trace a total of 11 metallicity chemical species in gas and stars. Star formation happens in dense, self-gravitating molecular clouds, and we also simulate energetic feedback from supernovae, stellar radiation, and stellar winds. So now that I've talked a little bit about the tools that I use, now I'm going to talk to you all about this first work that I did in connecting the metallicity gradients of dwarf galaxies to their age. So in particular, if we look at dwarf galaxies, at least in the local group, they all exhibit negative stellar metallicity gradients. So what that means is that the interior regions are really inhabited by these metal-rich stars, and as you move out to the outskirts of the galaxy, you start to see that they are inhabited by mostly metal-poor stars. And so you can see that here in this figure for a few local group dwarf galaxies. You see there the difference in their metallicity with respect to what it is at the center. And as you go out, they sort of fall off. Now, some previous work suggests that the strength of this gradient, right, how steep this slope is really determined by a galaxy's environment. And you can see that dwarf irregulars that generally lie a little bit further from the Milky Way and Andromeda tend to have these sort of flatter gradients, while the dwarf spheroidals that lie a little bit closer seem to have a steeper metallicity gradient. And so what I do in this work is really investigate potential formation mechanisms that can help us understand the diversity in these gradients. What really sets this diversity? So to look at this, I use a suite of isolated field dwarf galaxies run with the Fire 2 simulations. 9 of them are introduced in Fitz et al., while 17 of them are introduced in 2019 by Andrew Grouse. And so their virial masses range between 10 to the 10 to 10 to the 11 solar masses, while their stellar masses range between 10 to the 5 to 10 to the 9 solar masses. And so I say these are isolated dwarfs, but really that means that they are sufficiently far away from equal or greater mass companions. Okay, so they are still in their cosmological environments. They are still accreting mass from smaller or less massive galaxies, but in a cosmological sense, they are sufficiently isolated. And so if we look at these 26 dwarfs, we do see that they exhibit these negative stellar metallicity gradients. These gradients also have a diversity of strengths like we see in those local group dwarf galaxies. Here on the left is an example of a strong metallicity gradient, or sort of a steep gradient, you could say. And on the right-hand side is an example of a weaker gradient, or a sort of shallow metallicity gradient. Now in this work, we connect the formation of these metallicity gradients to this sort of feedback-induced or feedback-driven stellar migration. This is a figure from Karim El-Badri's 2016 paper that looks at some of the fire simulations and shows that for these fire galaxies that are going through these sort of cycles of star formation. If you look at stars that have lived through more of these star formation cycles, they will preferentially migrate further out than their younger counterparts, these stars that have lived through fewer of these cycles. And so if we assume that the older stars are metal poor while the younger stars are more metal rich or more enriched, then you can sort of imagine a picture where this star formation feedback really drives the formation of gradients. And so within this picture, you could really think about connecting the stellar age of a galaxy to the gradient that it has. And that's exactly what we do. So here I'm plotting the metallicity gradient on the y-axis as a function of T50, which is just the median stellar age of a galaxy. And we see that older galaxies tend to exhibit stronger gradients. And so this is a fairly tight relation within the simulations. And so, great, you might be thinking, that's cool. This happens within the Fire 2 galaxies. But does this relationship exist for real local group galaxies? And so to do that, we take from the literature metallicity gradient measurements, as well as T50 values taken from star formation histories of the same galaxies. And we see that for some of these local group galaxies that we're seeing here, they do tend to follow a very similar relationship compared to what we see in the simulations. Now, a little bit more of a subtle point here is remember that the simulated galaxies here are of isolated galaxies, right? The simulations are of isolated galaxies, but if you look at some of the real galaxies that I plot on this figure, many of them are satellites of the Milky Way. So this in and of itself points to the fact that this GSGA, gradient strength galaxy age relation, arises as a result of nature, right? These sort of internal processes of the feedback that galaxies undergo throughout their lifetimes. And really, if it plays any role, environment plays a sort of a secondary role. Yep. So did I look at this? Okay. So the question was, repeating it for the folks on Zoom, is did I look at the star formation histories if they're more bursty? At least for a lot of these fire galaxies, they do have very temporally bursty star formation histories. So you'll see sort of a bunch of supernova go off, and then the star formation sort of goes down to zero. You'll get another peak of star formation, and so it's very bursty over time. Yep. There's another question in the back. Yep.
So, there's a huge range of masses of the galaxies that you were including in your analysis of the fire simulation. And presumably range masses for these galaxies. So I know in the mass range of 10 to the 9 to 10 to the 10, so it's a higher mass end.
Sure.
The fire simulations have too much burstiness. The feedback's too strong, or whatever the reason is, right?
Right. What we see in the data. So okay.
Surely there's a dependence then on mass. Lower masses, maybe you do get that excess burstiness. Do you see differences in these gradient relations?
That's a good question. So to repeat that, the question was, so fire is sort of known for its very bursty star formation prescription. And so at the higher mass ends, do we see sort of a difference in the gradients that we get? And the answer to that, the short answer to that is, I think, yes. So specifically, I focus on these lower mass galaxies. But from what I know of the more massive end, these gradients do tend to go away at these larger masses. However, I haven't specifically looked at that in detail. Yep. So right, as I mentioned, this connection between the galaxy's gradient strength and the stellar age of a galaxy really points to the fact that this relation can arise due to nature, and the environment plays a secondary role, if anything, on setting this scaling relation. Now, since we published this work, there has been follow-up on both observational studies and other simulated studies that really tell us that there is a lot more work to be done here. And if you're interested in talking about the results of these papers, let's please talk about this after. But just for the sake of time, I'm going to go ahead and move forward. But it's interesting that this has sort of sparked a little bit of a conversation, and it's great to know that there is a lot more work to be done here. So I'm going to go ahead before I move on. I'm going to pause to see if there's any more questions. We did get a couple here, but before I move on to the next project here, are there any other questions, maybe online or? Yes.
So I feel like this explanation that it is nature that sets the gradient kind of intuitively makes sense, and like it was kind of how stars are forming inside the galaxy, and that's kind of sets the time and also the Eurasian cycle to set the slope. So I was just wondering, kind of, are there any external processes that you would have expected might have like played a role here, or kind of what would have been kind of the alternative if it wasn't
Right,
nature?
right. Yeah. So the question was, were there any external processes that could have potentially or, affected the relation that we're looking at here? And the answer to that is, I think some folks thought that maybe environment could play a role in such a way that galaxies that are around more massive companions will have a lot of their outer envelope stripped, right? And so that will in turn flatten these gradients. And that could potentially happen, I believe, in really placing them on this relation. However, as it stands, I think the relation sort of arises from this nature or these internal processes. But that's not to say that environment can't play a role, right? It could potentially play this sort of secondary effect on these galaxies, a secondary role.
I guess it would be an environment where you would continue kind of forming stars when you like come closer to a more massive galaxy, and which is probably not the case for most of the Milky Way systems.
Right, right, exactly. Yeah, Mike.
Do you have a sense of the magnitude of the error bars on the x-axis in this diagram?
Yeah, so I think in this diagram, I believe that they're smaller than the size of the points that we're using. But I need to go ahead and look back at that, and we can talk about that later. But I don't, off the top of my head, remember exactly sort of the rough scale of them.
So I want to try to get a sense of, in these dwarf galaxies, you're talking like stellar masses of like 10 to the 6-ish, 7, right?
Right.
So the gas is pretty well mixed, right? And typically at these low masses, the gas metallicity gradients are fairly flat.
Right, correct.
So is the reason why this steep gradients happen for older galaxies, is it that you're basically, you have like a flat core and you're like just like creating an extended disk of stars that were not born in situ? Like what does have you looked at like the profile of the fraction of the stellar mass that comes from in situ versus, radial migration?
Right.
And is it like very high in the outskirts?
I see. Yeah, that's a really good question. So I haven't looked at that in particular. So the question was, have we looked at sort of the gas and how that has affected the gradients in these low mass galaxies? Do a lot of the stars in the outskirts, are they really in situ stars that formed, or are they stars that have come from outside, right? Is that the question, if I'm getting it correctly? Yeah. So I think that's a good question. I could absolutely look into that, but that's not something that we looked into for this work. All right, if there are no other questions, I will go ahead and move forward. So the second project that we did that I did during my time at UC Irvine was looking at the radial acceleration relation and using it as a tool really to compare, or I guess discriminate between lambda CDM and MOND. As most of us might know here, modified Newtonian dynamics really is an alternative to dark matter. However, when we talk about MOND, there are two general schools of MOND that folks refer to in the literature. The first is MOND modified inertia. This is where we take Newton's second law, we change it below some characteristic acceleration. On the other hand, we also have modified gravity theories of MOND. This is where we can change the Poisson equation also below some characteristic acceleration. For the purposes of this talk, however, when I talk about MOND, I am going to be talking about modified inertia theories. So that's what I'll be talking about when I refer to MOND. So MOND modified inertia theories do a really good job at explaining these sort of flat rotation curves that we see in rotationally supported galaxies. They also sort of predict some scaling relations. One of these scaling relations is a radial acceleration relation, which connects the inferred acceleration of the total mass or the observed mass, right, inferred from rotation curves, to the gravitational acceleration that the baryons should feel within the galaxies. And so for about, just a little under 3,000 points within 175 galaxies in the SPARC data set, we do see a very strong relationship between these two properties, or these two quantities, I should say. And surprisingly enough, this sort of fit to the data can be derived within a Mondian framework, this Mond modified framework, such that above some characteristic acceleration that lies at about 10 to the negative 10 meters per second, you get what we expect from Newtonian dynamics, right? We get this one-to-one line, or a lot of these galaxies lie on this one-to-one line. However, at lower acceleration scales below this characteristic acceleration, we see that the data follows this scaling of about a baryon to the 1/2. Now, I want to mention and want to stress that under this formulation, the radial acceleration relation must be monotonic, meaning that as the baryonic acceleration increases, so too will the total or the observed acceleration. Okay. Now, the fact that all of these galaxies lie on this tight relation that can be described or predicted by Mond really begs the question: how could this relation arise from a lambda CDM universe? Yes.
How is the acceleration and the observed acceleration measured?
The observed acceleration relation, it's measured from the rotation curves of these galaxies. It's derived from the rotation curves, yes. So what we do is we sort of introduce some very simple analytic model in which we gather some expectations for what the radial acceleration relation should look like for different kinds of galaxies. And what I mean is different density profiles. So it turns out that we can track a galaxy's density profile and map it to an acceleration profile, and finally get what we should expect to see in radial acceleration space, this acceleration total versus acceleration baryons. And so for density profiles that we should expect for baryon dominated inner profiles, so this is more of like these rotationally supported galaxies, right, that have flat rotation curves on the outskirts, and then eventually their baryons reach some Keplerian scaling, we get rising acceleration as the radius decreases, right? From outside to in, the acceleration will rise. And so from that, we can get a scaling in the radial acceleration space that matches what we see in Mond, right? But as most of us know, as many of us know, baryon-dominated galaxies aren't the only kind of profile that we see in these galaxies. Is there a question? Oh, sorry. So it turns out that we can get this scaling too from dark matter-dominated cuspy profiles. So again, if we have a cuspy inner profile for the observed and the total, or excuse me, the total mass and the baryonic mass, then we can still get something that matches the Mond scaling. And so you can see more of this in detail in Julio Navarro's 2017 paper. Finally, if we look at dark matter dominated galaxies that have chord inner profiles, right, you have this sort of flat inner dark matter density, or excuse me, total density profile, then you get something different, right? For a constant density core, you get a peaked or a double valued acceleration profile. And this change in the profile is enough to change the radial acceleration scaling. Now, remember, I talked about how within a Mondian framework, the radial acceleration should be monotonic, right? That the accelerations, both accelerations, the total and the baryonic, should increase as you go in closer to the galactocentric rate, or excuse me, the galactic center. However, for dark matter-dominated galaxies with chord profiles, we should expect to see this non-monotonic radial acceleration track, where you have this rising and then falling hook that we're going to be referring to. Okay, so I'm going to call these sort of hooks that we expect to see for dark matter-dominated chord galaxies. Now, this is great. We sort of predict these hooks for these types of galaxies just using a very simple analytic model. However, it's interesting to see if we see these in maybe some of the simulations that I'm looking at. And so I do just this. So I take 12 simulated galaxies that are comparable mass to the Milky Way, and 8 simulated dwarf galaxies that have stellar masses below about 10 to the 10 solar masses. So what we see here is the radial acceleration relation in the points, the colored points. These are the tracks for the 20 simulated galaxies that we're looking at. The points are color-coded by the distance from the center. So yellower points lie closer to the center of the galaxy, while these purple points lie further out. And what we see, at least at high accelerations, right, we do get this sort of one-to-one scaling that we expect. However, at these lower accelerations, we do fall off in a very similar way to the observed data. And so you can kind of see that 2D histogram in the background. That is the observed radial acceleration relation. And so these simulations, we get this RAR out of our simulations. And so with these simulations, we know the mass, right? We're given the mass. And so assuming circular orbits, we can get the total acceleration for all the mass in the galaxy. And we can also get the baryonic acceleration from just the baryons. And so we get a radial acceleration relation that has a very similar normalization and scatter to what we observe. And this black line here is actually that Mond fit that we saw earlier. So that's really awesome. We get the radial acceleration from a lambda CDM universe, right? But remember, we also predict that there should be deviations from this Mondian predicted relation, and there are these hooks. So if we look at around 10 to the minus 11 meters per second square, we do see sort of some of these hook features that I had mentioned earlier. So to take a little bit of a closer look here, I plot just for a subset of the simulated galaxies, the radial acceleration. So, and I color code these lines with respect to the inner dark matter density slope. So how chord or cuspy are these profiles? So a chord profile will look a little more purple, while a cuspier profile will look yellow. Then I look at their individual total accelerations, their baryonic acceleration profiles, and then finally the total density. And we see that these purple lines, consistent with these constant density cores, are the ones that are exhibiting these hooks. So we're able to show, one, that not only this radial acceleration comes out of a lambda CDM universe, but we also predict these hooks that sort of deviate from this Mond predicted relation, right? This monotonic relationship that Mond expects, we should see hooks that fall off of that, or that hook off of that. So great. Now the question is, right, does this happen in real galaxies, right? And so the short answer to that is, if you take the spark data and just plot some of their tracks on the radial acceleration relation, you see some hook features here, right? And so we see these downward hooks happening in about 15% of the spark galaxy data. And we see a surprising number of upward hooks like this green one here for about 5% of the data, right? And so it's interesting to note that if you just take the spark data and plot it, you see some of these hooks. However, these are low mass galaxies, and it's sort of up in the air whether we should trust whether these hooks are there or not, because it's much more difficult to measure the accelerations in these inner regions of these galaxies. So we plot this not to say that, hey, Mond is wrong and lambda CDM is correct, right? But I think it really should be motivating us to do a little bit more work to determine whether or not these hooks are actually there, or if they're just some artifact of observational uncertainty. So that's sort of where I leave there. I'm going to go ahead and, oops, sorry about that. I'm going to go ahead and give a quick summary of what I've talked about so far. Internal processes are responsible for the gradient strength galaxy age relation and the radial acceleration relation. The gradient strength galaxy age relation arises in low mass galaxies from stellar migration caused by repeated star formation events, such that galaxies with older stellar populations will have these stronger metallicity gradients. in what we looked at, the radial acceleration relation arises due to the interplay between baryonic feedback physics and this sort of gravitational effects of the underlying dark matter distribution. But we expect deviations from what the Mondian framework predicts for galaxies that exhibit feedback-induced cores in their profiles. So this is sort of what I've talked about so far. I'm going to take a moment to pause again if anyone has any other questions before I move on. Yes.
The Mondian expectation for the radial acceleration relation, does it depend on density profile? You need to assume for the baryonic.
So does the Mondian expectation, so I'm going to go ahead and go back. So
Out the minus n, does it depend on n or the type?
No, so within this sort of modified theory, they just modify Newton's second law. So here they're just saying that with below some characteristic acceleration scale, below that, we're not going to get Newtonian mechanics, regardless of what that profile looks like. We're going to get something that scales as a to the minus 1/2, or a baryon to the minus 1/2. So it's
A0 does not depend on the density.
No, that's a parameter, a free parameter that they fit here. So if you look at Newton's second law here, you have mass times the acceleration, and you have some function mu here that is an arbitrary function that connects the high acceleration scales and the low acceleration scales. And so
in principle, stars themselves had a fairly flat density profile. They would also give you a vote if they're just by themselves. I mean, presumably that's not what we see.
Yeah.
Stars by themselves, right?
It was just the stars by themselves.
Or the baryonic mass.
Right.
Was a pretty flat profile.
You would expect to see sort of rising and falling.
But it has to be at the right acceleration.
It has to be at that acceleration scale.
So, you know, it's not an arbitrary number you get out.
Right.
Yeah, I mean, presumably you measure it and it doesn't work, but in principle, the stars themselves could be.
Right. Yeah. Gonna go ahead and move us back up. Sorry about this. I moved a little further back. Great. So with that being said, all of that has been, I've been talking about the work that I've done to sort of look at how scaling relations arise due to nature, right? The nature of galaxies. Now, more recently, in the work that I'm doing as an NSF fellow at Pomona College, I have started to use a large volume simulation to understand nature. So very recently, the FIRE collaboration has put out a larger box simulation run at with the FIRE2 feedback implementation. So this box on the side has about 22, has a side length of about 22 megaparsecs. And it resolves about 1,000 galaxies with stellar masses greater than 10 to the 8th solar masses at a resolution comparable to some of the zoom-ins that I was showing before. So it gives us a larger sample to look at. And so now the question that I want to answer with this sort of larger scale simulation is how does environment affect certain scaling relations, right? Now we're moving to the nurture portion of this. And so I just want to share some preliminary work that I've been working on with the Firebox data. And so it turns out that the Firebox has about 1,700 galaxies above 10 to the 6 solar masses with about 128 particles or greater. And the relations I want to look at here are the size-mass relation and the relationship between the dark matter mass and the stellar mass. And so these masses are within the stellar half-mass radius of these galaxies. In triangles, you'll see the satellites plotted in the satellites in the Firebox, and the circles show the centrals in the simulation box. And so I've color-coded all of these points with two different parameters. On the left-hand side, it's color-coded by this parameter called beta, which is just the log distance from the average or the running average for the centrals. So what this beta parameter is telling you is that is how puffy a galaxy is compared to other galaxies of similar stellar mass. On the right-hand side, I'm showing something similar for the dark matter mass and the stellar mass. Here, this gamma parameter is telling us how dark matter concentrated, or how dark matter dominated, or dark matter deficient a galaxy is when compared to other galaxies with the same stellar mass. And so the question really that I want to answer is, how does a galaxy's environment change or determine where a galaxy might lie on these relations? And so the first thing I want to show here is just if we plot these two parameters as a function of each other, so there's beta as a function of gamma, we get a couple, we can split the space up into a few different quadrants. So I should say that all of these points are color-coded by what I'm calling distance to massive galaxy, and that's just the distance to the nearest galaxy with a virial mass of 10 to the 11 solar masses. That is it's an arbitrary choice. I can play around with that moving forward. But there are four different quadrants. The first quadrant is that we see dark matter-dominated galaxies, and they're puffy. In the second quadrant, the galaxies are dark matter underdense and puffy. The third quadrant, the galaxies are dark matter underdense and compact. And then finally, as you could expect, the bottom right quadrant gives us dark matter-dominated galaxies, and they are also compact. And so what we see first off is that we can kind of see that the satellites preferentially inhabit this sort of second quadrant, this dark matter underdense and puffy. But in aggregate, we don't really see much of a relation between these two quantities. However, if we get rid of the satellites, right? So yeah, there's no clear relationship here. But if we get rid of the satellites, we see something interesting in that the centrals that are further away from massive galaxies, or these more isolated centrals, tend to have some relationship. So as you get more dark matter dominated, you do seem to get a little bit puffier. But then as you get closer and closer to a more massive companion, you start to see that there's this track that these galaxies start to travel into, that these satellites like to inhabit, right? So to see a little bit more of how the environment plays a role in, yes, is there a question?
Like with, instead of like using the same mass for all of them, using like some fractional mass, like within some radius of a galaxy that's 100 times its mass.
So I haven't tried that. I think that's a really good, interesting point, and I can definitely try that. So this is all preliminary work that I've been working on. So I can absolutely try and play around with the sort of space that we're looking at here. So to dig into this a little bit more, I plot this beta parameter as a function of the distance to the nearest massive galaxy. And this time I'm color coding by this gamma parameter. And so what we see is that we do see some relation between how puffy a galaxy is and how close it is to a more massive companion. The galaxies that lie closer to massive companions will tend to be puffier, and as you move further away, they tend to get more and more compact. But something that's really interesting here, just qualitatively, it does seem like this gamma parameter might really be setting the scatter here. Now, I haven't looked much more into this, and I'm going to do more work on this as we move forward, but I just wanted to show some preliminary work, and I'm meeting with some of you all later today, so please feel free to chat a little bit more about this with me, and I'd be happy to hear more ideas on where to go from here. So some other questions that I do want to consider moving forward is, how do global properties change as a function of environment, right? So how do other global properties, not just the size, not just the masses, but things like formation time, chemical composition. Another question is, how does environment affect a galaxy's position on the relationships I talked to you all about earlier, the GSGA and the radial acceleration relation? So now that I have more galaxies at my disposal, how does environment play a role in changing what these relations look like? And then also I'd like to ask really, what can Firebox teach us about the faintest, most isolated galaxies? And so these questions are very important, specifically because of the telescopes that are up and coming, the Vera Rubin telescope and some of the very large telescopes that we're seeing built and will be coming online in the near future. And so one thing you might see is that I have highlighted a couple of these questions. Specifically, I will have a Pomona College surf student working with me this summer that will be looking into the question of formation time, right? Does the environment play a role in this formation time? And so Brian Calderon, who is a sophomore at Pomona College, will be working with me this summer to ask this question. Now, this bottom question is planned. It's a planned project that Jorge Moreno and I have both been discussing to resimulate these low density environments in Firebox at higher resolution to really ask that question, how does environment play a role on, how does environment affect these sort of faintest galaxies that we're going to be seeing? And so the plan is to sort of get a couple of these lower density regions in Firebox, rerun them at higher resolution. This summer, an undergrad at Pomona College will also be working on first just identifying some low density regions in Firebox in particular, just to see which regions might be interesting to resimulate. Okay, so I'm gonna pause here. I think I do have a little bit of time. Are there any questions so far with what I've talked about here before I talk about the last thing? Yes. Okay.
But when you're simulating this low density environments, are there kind of at matching resolution higher density environments for kind of apples to apples comparison?
We would like to resimulate these at least, you know, latte resolution. So some of like the zoom ins that we're looking at, resimulate them at those resolutions. Yes.
I guess my question was like, do you also have a higher density environments just at the same resolution?
Right, right. Yeah, so I think there is work being done within the fire collaboration to do that. I'm not, I think, with the fire simulations, but I'm not super plugged into that conversation. All right, so with the last few minutes that I have here today, I want to talk to you all about some of the broader impacts work that I proposed for the NSF that I'm really excited about. And really, it's about nurturing young scientists and uplifting marginalized scientists. I'm very passionate about doing this stuff. And so to do this, what I'm doing is I'm actually teaching the Astro 2 Galaxies and Cosmology course at Pomona College. And within that course, aside from covering the normal astrophysics topics, another topic that I want to discuss is really these sort of issues of when it comes to justice within the astronomy community. So I like to really be clear that astronomers, academics, scientists are people first. And we are also, just like the galaxies I've been talking about, we are also affected by our environment, right? And so we, I think, have an obligation to make sure that other folks in our environment are succeeding as much as we are. And so within this class, we have weekly community justice discussions on different topics. So this past week, we had a discussion on the notion of laziness, right? Is laziness even real? And thinking about how we can change our mindset a little bit. And rather than thinking of, hey, this person is lazy, maybe we think about what is affecting them. Why are they unable to maybe produce, or if they're in a class, let's say a student is not submitting homework, is not submitting some assignments, rather than saying the student is lazy, I'm gonna fail them, maybe I should be asking the question, right? What is happening in their lives that is affecting them and how can I help them? And so we have very similar, these sort of discussions about issues that really affect us as academics and scientists. So this is sort of the first portion of this Astro Uplift project that I proposed. So at the end of this semester, the students are going to conduct research on a couple of things. First of all, looking at astronomical discoveries by marginalized folks in astronomy. Another thing that they'll look into is just our methods to dismantle barriers that are operating against marginalized folks. And so the students will all do this in group projects. They will present at the end of the semester, really short, some short presentations. And all of this content is going to be taken to be used for planetarium shows in the future. So Pomona College is a very nice planetarium. And so the plan is to take the content that the students are building in this project and build planetarium shows that are really at the intersection of astronomy and justice. So I'm really, really excited about this project as I move forward. As I mentioned, I just started in August, and so this is sort of just the first step in teaching this class. But one thing I'd like to say is just if this is not something that you think about every single day, I really challenge you all to think about how we as individuals and as a community can make our environment safe and conducive to great work from folks of any type of background. So I'm going to go ahead and end with a summary. Internal and external processes can have varying effects on galactic interiors. These effects can dictate a galaxy's position on a number of scaling relations, and we can really use these scaling relations as tools to disentangle the effects of nature and nurture. And really developing a detailed understanding of this interplay really puts us in a unique position to use these scaling relations as a basis of tests for galaxy formation and, and for dark matter models with more focused experiments with simulations in the future. I'd like to thank you all for your time, and I'll go ahead and take any questions now. Thanks.
Any question? All right, Mike. Wait for the mic.
Thanks for the great talk. So you demonstrated that the simulations, yet again, are reproducing the sort of Mond phenomenology. And to put on my Stacy hat, his $1 million question is why, right? What is the physical explanation? Why do we have this magic acceleration scale A naught? And, there have been various works and people thinking about this and how this might work in a lambda CDM context, whether it's feedback or cosmological ICs or whatever. Where do you stand on this right now?
Yeah, I think that's a really good question, is sort of why do we get this sort of scaling relation? And I don't know, I kind of see this more of it seems to be very coincidental that, we do get this bend off of the one-to-one at the same scaling relations. And so particular, I have not thought too much about sort of why we get this, but really, I think the interesting question is that fall off really seems to come from this sort of interplay between this feedback energy and also the gravitational effects of the density profiles or the dark matter density profiles that we see in these galaxies. But yeah, I haven't thought too much more about, exactly why are we getting this at that scale that Mond has predicted.
Thanks.
Thank you very much. It was very interesting. My first question is related to what Mike asked. And sort of, I was wondering whether similar type of studies have been done with other hydrodynamic simulations, and whether the same kind of qualitative results are found there, or is it a difference between the subgrid models that we should think about and care about?
Right. Yeah. So there has been work done on different simulations with varying degrees of success. So some simulations reproduce a very similar normalization, right? But the scatter is very different. And in that case, it might be sort of the resolution, or in this case, so a lot of the fire simulations really resolve this star formation at these very, very small scales, while other simulations do not do the same. So it could be something like that. Other simulations will get some relationship between the two accelerations, but it might not bend off in much of the same way. So there has been work done here, and I think really the question might lie under what physics is actually simulated and at what resolutions.
I see. Thank you very much. And can I ask another question about the uplift?
Yeah.
A very short question. So you mentioned there that the students, can you go back to the slide about the uplift?
Oops. This one or the next?
The next one. Yeah, so you mentioned that they're going to study methods to dismantle barriers operating against marginalized communities. And the question is, where do these methods come from? Is there like summary of good methods?
Yeah, I think that's a good question. So I think the short answer to that is there's not sort of a guidebook for how to do this, right? However, there is research done on other topics, such as peer mentorship is one that comes to the top to my head. There is research done on how peer mentorship affects not just the mood of folks in communities, but also how much they produce in those communities. So things like that there is literature about, but there's not sort of a list on things to do to support these. That's the concept. Yeah.
I don't have a very well-formed question,
Okay.
but I'm thinking a little bit about what you've said here. So don't leave this slide.
Okay.
In that, let me see if I can form this. So for this is really an excellent thing to do. Mm-hmm. My question to you is, for a number of people, barriers come from past or even ongoing trauma. Mm-hmm. And I'm curious how you've designed your program to thread that needle to keep a safe space for people mm-hmm. who sometimes just want to be in a space free from the trauma.
Right.
Versus acknowledging so that people can be seen and authentic. Mm-hmm. Mm-hmm. And I don't teach in a classroom. You have many more people in a classroom than when I have one or two people in my office, usually zero, but sometimes one. And so I'm curious how you approach that, because that trickles down in all of the kinds of spaces we're trying to mentor in, Absolutely. Be peers in, be supportive in.
Absolutely. Yeah, I think that's a very, very good question and an important one to consider, right? I think it is very real that many people are informed by their experiences and the trauma, and a lot of the times it's trauma, right? And so at least within the class, to set a safe environment, I do have working expectations that I show at the beginning of each class to remind folks that we are all coming from different backgrounds. And so to be cognizant of that and to really leave any assumptions or any preconceptions at the door, be as open as possible to listening to people, right, hearing that. And I think really setting the tone for that environment is extremely, extremely important at all skills, whether you're in a classroom or right in an office with a couple of people. And so I think really explicitly mentioning that at the beginning of any relationship is very important, making sure that they understand that one, it's good to listen, be cognizant of your experiences and other people's experiences. You might not agree on certain things, and that's totally okay, right? I think it's also important to remind folks to think about how they are positioned to help folks near them, right? So yes, some folks will come in with trauma, other people will come in with privilege, right? And so thinking about how you and where you stand, how you can be really a resource to others. And I think that's a really important thing to remind folks as well. So I guess the short answer really is setting these expectations ahead of time, knowing that this is a safe environment. This is, we're expected to keep this environment as open as possible, as important. And I think it's also important to just remind folks that if they do need to step out, if they are uncomfortable with any conversations, it is okay to step out if they need to.
Thank you.
Any final questions?
Thanks. That was an awesome talk. And I love this idea and how you're going to turn it into a planetarium show.
Yeah.
I guess I have a science question.
Okay.
For the very beginning, when you were talking about like metallicity gradients, etc., I was wondering if you did any cuts on observability, since in simulations we have full access to all the star particles, but in observations we can only see a subset of the stars, right?
Right.
I was wondering if potentially you've looked into that and like it could explain why there was a shallower gradient, it looked like, in the observations versus the simulations.
Yeah, that's a really great question. I did not look into that. I did not make any cuts. I just sort of took the quote perfect data that we do have in the simulations. But I think that's a really interesting question to ask moving forward. I mean, we do need to think about the observability and how that has affected measurements that we've made so far.
I guess I'll ask as well, since it's kind of connected. I had this in my mind. I mean, for the gradient age relation, if you asked me ahead of time, I guess I could have said, well, maybe it's migration, maybe it's in situ star formation, like Guillermo was mentioning, maybe it's accretion. So for different scenarios, I would guess there's other observables that you could compare to. Do you have the resolution in these? For example, would there be an expectation of different stellar populations as a function of radius for the different scenarios that could have produced the metallicity gradient?
Right. So I guess, correct me if I'm wrong. So the question you're asking is are there different scenarios depending on the different populations that could have created these gradients? Is that?
Yeah, or vice versa. Would you expect different stellar populations as a function of radius? And is that something you can predict through the simulations
that's
to
interesting.
compare?
I think I need to think about that question a little bit more to give you a more solid answer, but I'm not super sure about that
yet. Okay. Thank you.
Yeah, thanks.
All right, let's thank Francisco again.
Thank you all.
Yeah, that's the thing about these simulations. There's always more to do, right? There's just so much stuff. Let's see. Did you turn it off? Test?
Oh, I didn't. It's still.
I don't know.
I can tell which one is.
Hello? This may be mine. You gotta like test. Test.